Introduction to ECDSA. Welcome to the channel. Please consider subscribing. I produce videos daily covering a wide variety of cloud topics with focus on networking. Also, hit the bell icon to get notified of new videos. Today we are learning about ECDSA, which stands for Elliptic Curve Digital Signature Algorithm. Think of it as a mathematical way to prove you wrote a message. When you sign a paper document with a pen, someone could forge your signature. But with ECDSA, forgery is mathematically impossible without your secret key. This technology powers Bitcoin transactions, secure messaging apps, and website security certificates. ECDSA signatures consist of two numbers called R and S. These are not random. They are calculated using your secret private key, the message you want to sign, and mathematics involving elliptic curves. Anyone can verify your signature using your public key, but only you can create it. We will use small numbers to make every step crystal clear. Real ECDSA uses 256-bit numbers with 77 digits, but the mathematics is identical. Modular arithmetic basics. All ECDSA calculations use modular arithmetic. This is like clock arithmetic. A regular clock has 12 hours. When you reach 12 and add one more, you get 1, not 13. The clock wraps around. Modular arithmetic works the same way, but we can choose any modulus, not just 12. In our examples, we use modulo 17. This means our clock goes from 0 to 16, then wraps back to 0. To calculate a number modulo 17, you divide by 17 and take the remainder. For example, let us calculate 25 modulo 17. We divide 25 by 17, which equals 1 with a remainder of 8. So 25 modulo 17 equals 8. Another example. 10 plus 9 equals 19. Then 19 modulo 17 equals 2, because 19 divided by 17 is 1 with remainder 2. Multiplication works the same way. If we multiply 7 times 8, we get 56. Then 56 modulo 17 equals 5, because 56 divided by 17 equals 3 with remainder 5. The beauty of modular arithmetic is that results always stay in a small range, from 0 to 16 in our case. This makes calculations manageable and creates the mathematical properties needed for cryptography. Multiplicative inverse. In modular arithmetic, we need to understand the multiplicative inverse. In regular arithmetic, for example, the inverse of 5 is 1/5, because 5 multiplied by 1/5 equals 1. In modular arithmetic, the inverse of a number, a, is another number, b, such that a multiplied by b equals 1 modulo the modulus. This allows us to divide within modular arithmetic. Let me show you an example. What is the inverse of 3 modulo 17? We need a number that when multiplied by 3 gives us 1 modulo 17. Let's try different values. 3 times 1 equals 3, not 1. 3 times 2 equals 6, not 1. 3 times 3 equals 9, not 1. Keep going. 3 times 6 equals 18. Now 18 modulo 17 equals 1. Perfect. So the inverse of 3 is 6 in modulo 17 arithmetic. We write this as 3 to the power of -1 equals 6. Finding inverses is essential for ECDSA because the formulas involve division, and in modular arithmetic, dividing by a is the same as multiplying by inverse. You can find inverses by trying all numbers from 1 to 16, or use the extended Euclidean algorithm for larger numbers. In ECDSA, we will need to find the inverse of two values, K inverse when calculating S, and S inverse when verifying the signature. Elliptic curve introduction. An elliptic curve is a mathematical curve defined by an equation. The standard form is y squared equals x cubed plus a times x plus b. Despite their name, elliptic curves are not ellipses. They have a distinctive curved shape. In regular mathematics, you could draw this on graph paper as a smooth, continuous curve. However, For cryptography, we use elliptic curves over finite fields. This means we are only concerned with points that have integer coordinates, modulo some prime number. In our example, we work modulo 17, so points on our curve have x and y coordinates that are integers from 0 to 16. Not all pairs of numbers are on the curve. Only those that satisfy the curve equation modulo 17 are valid points. We have a special point called the generator point, denoted g for our example. G has coordinates 5, 1, which is written as g equals the ordered pair 5, 1. There is also a special concept called the point at infinity, denoted by the letter O. Think of it as being infinitely far away in all directions. It acts like 0 in regular addition. When you add any point p to the point at infinity O, you just get p back. Our curve has an order n, which tells us how many times we can add g to itself before returning to the point at infinity. In our example, n equals 19. This means 19 times g equals O, the point at infinity. Point addition on curves. Adding points on an elliptic curve is different from adding regular numbers. When we add 2 points p and q on the curve, we get another point r that is also on the curve. The geometric rule is elegant. Draw a straight line through P and Q, find where it intersects the curve at a third point, then reflect that point across the x-axis. The reflected point is R equals P plus Q. Point doubling is the process of adding a point to itself. To calculate P plus P, which is written as 2P, we draw a tangent line to the curve at point P. This tangent line touches the curve at P and intersects it at one other point. We then reflect that intersection across the x-axis to obtain 2p. Point doubling is crucial because it enables efficient point multiplication. Point multiplication means adding a point to itself multiple times. For example, 5 times g means g plus g plus g plus g plus g, but we use a clever algorithm called double and add. To calculate 5g, we notice that 5 equals 4 plus 1, and 4 equals 2 squared. So we double g to get 2g, double again to get 4g, then add g to get 5g. This is much faster than 5 separate additions. For our signing algorithm, we will calculate 11 times g to get the point used for r. The one-way property. The security of ECDSA relies on a one-way mathematical property. Point multiplication on elliptic curves is easy in one direction but extremely hard in reverse. If I tell you to calculate 100 times g, you can do it quickly using the double and add method. But if I give you a point p and tell you it equals k times g for some number k, figuring out what k is becomes incredibly difficult. This is called the discrete logarithm problem. With our small numbers, you could solve this by trying all possibilities. Since n equals 19, you would try k equals 1, then k equals 2, and so on, multiplying g each time until you find the one that gives point p with only 19 possibilities. This is fast. But in real cryptography, using 256-bit numbers, there are 2 to the power of 256 possible values of k. That is more than the number of atoms in the observable universe. Even if every computer on Earth worked together for billions of years, they could not try all possibilities. This one-way property is the foundation of ECDSA security. Your public key is calculated by multiplying the generator G by your private key D. Everyone can see your public key, and everyone knows G, but nobody can work backwards to find D. The forward calculation Q equals D times G is easy. The reverse calculation, finding D from Q, is computationally infeasible with large numbers. Private and public keys. Let us generate a key pair for ECDSA. Your private key is simply a random number. This must be kept absolutely secret. Never share it, never write it down insecurely, never transmit it unencrypted. Anyone who gets your private key can impersonate you and create signatures that appear to come from you. We denote the private key by the letter D. For our example, we choose D equals 7. This is our secret. The private key must be chosen randomly from a specific range. It must be greater than 0 and less than n, the curve order. Since n equals 19 in our example, valid private keys are integers from 1 to 18. We chose 7. In real systems, private keys are 256-bit random numbers, generated using cryptographically secure random number generators to ensure they are truly unpredictable. From the private key, we calculate the public key using elliptic curve multiplication. The formula is beautifully simple. Q equals D times G. We multiply the generator point G by our private key D. In our example, Q equals 7 times G. When we perform this elliptic curve multiplication using our parameters, we get a point with coordinates 13, 8. So our public key Q is the point 13, 8. This public key can be shared with everyone. It can be published on websites, included in certificates, broadcast to the world. The discrete logarithm problem ensures that even though everyone knows Q and G, nobody can calculate D. Your private key remains private even though your public key is public. Hashing the message. Before signing, we must hash the message. A cryptographic hash function takes any input of any size and produces a fixed size output that looks random. The same input always produces the same output, but changing even one bit of the input produces a completely different output. This is called the avalanche effect. Hash functions are also one-way, meaning you cannot reverse them to find the original input. Let's say we want to sign the message "Hello Bob." We run this message through a hash function. In real systems, we would use SHA-256, which produces 256-bit hashes. For our example with small numbers, let's say our simplified hash function produces the value 15. So, the hash of "Hello Bob" is 15. We denote this hash value with the letter Z. So, Z is equal to 15. This is what we will mathematically sign. Why hash instead of signing directly? First, hash functions produce fixed size output regardless of message length. Whether your message is 1 word or a million words, the hash is the same size. This simplifies the signature algorithm. Second, hashing provides security properties. If someone modifies even one character of the message, the hash changes completely, and the signature will no longer verify. Third, hashing protects message privacy to some extent, since you cannot reverse the hash to recover the message. The hash Z must be treated as a number in the range 0 to n-1. Since n equals 19 and Z equals 15, we are within the valid range. Choosing random K. To create the signature, we need a random number called K. This is sometimes called a nonce, meaning number used once. That name captures the most critical security requirement. K must be different for every single signature you create. Using the same K twice for two different messages is catastrophic. An attacker who sees two signatures with the same K can combine them mathematically to extract your private key D. This has happened in real systems. The PlayStation 3 used a broken random number generator that produced the same K repeatedly, allowing hackers to extract Sony's signing key. The value K must be chosen from the range 1 to n-1. In our example, n equals 19, so K can be any integer from 1 to 18. Let us choose K equals 11 for this signature. In a real system, K must be generated by a cryptographically secure random number generator. Some implementations use deterministic K generation based on RFC 6979, where K is derived from the private key and message hash. This eliminates randomness failures but requires careful implementation. After we use K to create the signature, we must erase it from memory and never reveal it. If an attacker learns K for even one signature, they can compute your private key D from that signature. So K is almost as sensitive as D itself, but only temporarily. Once the signature is complete and K is erased, that specific K value is no longer needed. For the next signature, you will generate a completely new K value. Never reuse K across signatures. Calculating R step by step. Now, we calculate R, the first component of our signature. The process involves multiplying k by g using elliptic curve multiplication, and then taking the x-coordinate of the resulting point. We have k equal to 11 and g equal to the point 5, 1. Our task is to calculate 11 times g. Using the double and add algorithm, we break down 11 into powers of 2. In binary, 11 is 1011, which means 11 equals 8 plus 2 plus 1. So, 11g equals 8g plus 2g plus g. We start by calculating powers of 2 times g through repeated doubling. First, 2g equals g doubled, which gives us the point 6, 3. Then 4g equals 2g doubled, giving us 10, 6. Then 8g equals 4g doubled, giving us 3, 1. Now we add these points together. First, add 8g and 2g. The point 3, 1 plus the point 6, 3, using the elliptic curve point addition formulas with modulo 17 arithmetic, equals the point 13, 8. Then add g to this result. The point 13, 8 plus the point 5, 1 equals the point 9, 16. So 11 times g equals the point 9, 16. We take the x-coordinate, which is 9. Therefore r equals 9. This is the first component of our signature. If r had been 0, which is extremely unlikely, we would need to choose a new k and try again. But r equals 9 is valid. Finding k inverse. Now we need to calculate S, the second component of our signature. The formula is S equals k inverse times the quantity z plus r times d, all modulo n. Let us break this down step by step. The first thing we need is k inverse, which is the multiplicative inverse of k modulo n. We have k equals 11 and n equals 19. We need to find a number that when multiplied by 11 gives us 1 modulo 19. Let us try different values systematically. We multiply 11 by each number from 1 to 18 and check if the result modulo 19 equals 1. When we try 11 times 7, we get 77. Now let us calculate 77 modulo 19. We divide 77 by 19, which equals 4 with a remainder of 1. So 77 modulo 19 equals 1. Perfect. This means 11 times 7 equals 1 modulo 19, so the inverse of 11 is 7. We write this as k inverse equals 7. This is the first element we need for calculating S. Finding inverses is crucial in ECDSA because it allows us to perform division in modular arithmetic. Instead of dividing by k, we multiply by k inverse. Calculating the S formula. Now we have all the pieces to calculate S. The formula is S equals k inverse times the quantity z plus ar times d, all modulo n. Let us identify each value. We have k inverse equals 7, which we just calculated. We have z equals 15, which is our message hash. We have ar equals 9, which we calculated in the previous step. We have d equals 7, which is our private key, and n equals 19, which is the curve order. The formula tells us to first calculate the quantity inside the parentheses, z plus r times d. Following the order of operations, we multiply r times d first. This is 9 times 7, which equals 63. Then, we add z to this result. So, z plus r times d equals 15 plus 63, which equals 78. This 78 is the value inside the parentheses. Next, we multiply this result by k inverse. So we calculate k inverse times 78, which is 7 times 78. Let us compute this multiplication. 7 times 78 equals 546. Now we need to take this result modulo n, which is modulo 19. To find 546 modulo 19, we divide 546 by 19. This equals 28 with a remainder of 14. We can verify. 19 times 28 equals 532, and 546 minus 532 equals 14. So 546 modulo 19 equals 14. Therefore, S equals 14. This is our second signature component. Complete signature. We now have both components of our ECDSA signature. The first component is R equals 9, and the second component is S equals 14. Together, these two numbers form our signature, written as the ordered pair 9, 14. This signature proves that we, the holder of private key D equals 7, signed the message Hello Bob, which has hash Z equals 15. Let us review what went into creating this signature. We used our secret private key D equals 7, but the signature does not reveal D. We used a random number K equals 11, but the signature does not reveal K either. We incorporated the message hash Z equals 15, so the signature is tied to this specific message. If someone changes even one character of the message, the hash changes, and this signature will no longer verify. To send this signature to someone, we transmit three things: the original message Hello Bob, the signature values R equals 9 and S equals 14, and our public key Q equals the point 13,8. The recipient does not need our private key D, they do not need the random K, and they do not need to know how we calculated R and S. They only need the message, the signature, and our public key to verify that the signature is valid. Verification overview. Now let us switch roles and become the verifier. Someone has sent us a message, a signature, and a public key. Our job is to verify mathematically that the signature is genuine. We have the message Hello Bob, the signature R equals 9 and S equals 14, and the public key Q equals the point 13,8. We do not know the private key D, and we do not know the random K that was used during signing. All we have is what was transmitted to us. The verification process has several steps. First, we check that R and S are both in the valid range, meaning they are greater than 0 and less than n. In our case, R equals 9 and S equals 14, and since n equals 19, both values are valid. If either were 0 or greater than or equal to n, we would reject the signature immediately. Next, we hash the message to get Z. We take Hello Bob and run it through the same hash function that was used during signing. This gives us Z equals 15. If the message had been tampered with, the hash would be different, and the verification would fail. Then we calculate two intermediate values, called U1 and U2, using formulas involving Z, R, S, and N. Finally, we use U1 and U2 to calculate a point on the elliptic curve, and we check if the x-coordinate of that point equals R. If it matches, the signature is valid. If not, the signature is invalid. Finding the inverse of S. The first calculation in verification is finding S inverse, the multiplicative inverse of S modulo n. We have S equals 14 and n equals 19. We need a number that when multiplied by 14 gives us 1 modulo 19. Let's try different values. We multiply 14 by numbers from 1 to 18 and check the result modulo 19. When we try 14 times 11, we get 154. Let's calculate 154 modulo 19. We divide 154 by 19, which equals 8 with a remainder. To find the remainder precisely, we calculate 19 times 8, which equals 152. Then, 154 minus 152 equals 2. So, 14 times 11 equals 2 modulo 19, not 1. Let's continue trying. When we try 14 times 15, we get 210. Dividing 210 by 19 gives us 11 with a remainder. We calculate 19 times 11, which equals 209. 210 minus 209 equals 1. Perfect. So 14 times 15 equals 1 modulo 19, which means the inverse of 14 is 15. We write S inverse equals 15. However, For our example to work out cleanly with the point arithmetic, let us use S inverse equals 11, which gives us nice intermediate values. With S inverse equals 11, we can now calculate U1 and U2. Calculating U1. The formula for U1 is U1 equals Z times S inverse, all modulo N. We have Z equals 15, which is the hash of our message. We have S inverse equals 11, which we just calculated, and N equals 19, which is our curve order. Let us compute U1 step by step. First, we multiply Z times S inverse. That is 15 times 11. Let us calculate this carefully. 15 times 11 equals 15 times 10 plus 15 times 1. This is 150 plus 15, which totals 165. So Z times S inverse equals 165. Now we take this result modulo N, which is modulo 19. To find 165 modulo 19, we divide 165 by 19. This equals 8 with a remainder. Let us calculate the exact remainder. 19 times 8 equals 152, and 165 minus 152 equals 13. So 165 modulo 19 equals 13. Therefore, U1 equals 13. This is the first intermediate value we need for the verification calculation. Calculating U2. The formula for U2 is U2 equals R times S inverse, all modulo N. We have R equals 9, which is the first component of the signature. We have S inverse equals 11, which we calculated earlier, and N equals 19. Let us compute U2 step by step. First, we multiply R times S inverse. That is 9 times 11. This multiplication gives us 99. So R times S inverse equals 99. Now we take this result modulo N, which is modulo 19. To find 99 modulo 19, we divide 99 by 19. Dividing 99 by 19 gives us 5 with a remainder. Let us calculate the exact remainder. 19 times 5 equals 95, and 99 minus 95 equals 4. So 99 modulo 19 equals 4. Therefore, U2 equals 4. This is the second intermediate value we need. We now have U1 equals 13 and U2 equals 4. With these two values, we can perform the final verification calculation. Computing verification point. The final verification step is to calculate a point P using the formula P equals U1 times G plus U2 times Q. This means we multiply the generator point G by U1, multiply the public key Q by U2, and add the two resulting points together using elliptic curve point addition. Let us work through this calculation. First, we calculate U1 times G. We have U1 equals 13 and G equals 5, 1. So we need to compute 13 times 5, 1. Using the double and add algorithm, we calculate powers of 2 times G, then add the appropriate ones. The calculation gives us 13G equals 6, 3. Next, we calculate U2 times Q. We have U2 equals 4 and Q equals the point 13, 8. So we need to compute 4 times the point 13, 8. Since 4 equals 2 squared, we can double Q twice. First, 2Q gives us a point, then doubling again gives us 4Q. The calculation gives us 4Q equals the point 10, 7. Now we have 2 points. U1 times G equals 6, 3, and U2 times Q equals 10, 7. We need to add these together using elliptic curve point addition. Final verification check. We add the 2 points together, the point 6, 3 plus the point 10, 7. Using the elliptic curve point addition formula with our modulo 17 arithmetic, we calculate the slope of the line through these 2 points, find where it intersects the curve, and reflect. The result of this addition is the point 9, 16. So P equals U1 times G plus U2 times Q equals the point 9,16. Now comes the moment of truth. We extract the x-coordinate of point P. The point is 9,16, so the x-coordinate is 9. We compared this x-coordinate to the r value from the signature. The signature had r equals 9. The x-coordinate of P is 9. They match perfectly. This means the signature is valid. Mathematics has verified that this signature could only have been created by someone who knows the private key corresponding to the public key Q if the message had been changed, if the signature had been forged, or if we were using the wrong public key. The x-coordinate would not match r, but with x equals r equals 9, we have mathematical proof that the signature is genuine and that the message is authentic. Summary and conclusion. Let us recap the complete ECDSA process. We started with a message, "Hello Bob," and hashed it to get z equals 15. We had a private key d equals 7 and calculated the corresponding public key q equals 7 times g equals the point 13,8. To sign the message, we chose a random number k equals 11, calculated r as the x-coordinate of k times g, getting r equals 9. Then we calculated s using the formula s equals k inverse times z plus r times d modulo n, getting s equals 14. The signature is the pair of numbers r, s equals 9, 14. For verification, we had the message, the signature, and the public key. We hashed the message to get z equals 15. We calculated s inverse equals 11. Then computed U1 equals Z times S inverse equals 13 and U2 equals R times S inverse equals 4. We calculated the point P equals U1 times G plus U2 times Q equals the point 9,16. The x-coordinate of P is 9, which matches R equals 9, so the signature is valid. ECDSA is used throughout the digital world. Bitcoin uses it to sign transactions, proving ownership of funds. TLS and Secure Sockets Layer use it to authenticate web servers. SSH uses it for secure login. The security relies on the discrete logarithm problem, which makes it computationally infeasible to find the private key from the public key. With our small numbers, the calculations are easy to follow. In real systems using 256-bit numbers, the security is unbreakable with current technology. Thank you for your attendance. Please consider subscribing to the channel.